Okay. Okay, so hi guys, I prepared quite a lot of information. Thank you for the introduction. So briefly, I am a camera system engineer and started to work with autonomous cars for last 5 years in US. And right now I want to speak about some safety metrics that cameras have. And some of these metrics I basically developed myself, and I want to introduce it and show how we use it when we're measuring the next, like feasibility of the next system. So please, next slide. Next, please. Yeah, we will speed up, so please try to. So we will cover 4 topics today. First will be image quality and metrics that we use. And second will be some perceptual metrics and analysis of translation, the image quality metrics from photography into the perception of autonomous cars. And then I will tell about system architecture, how cameras are connected and information is combined, compare it with some mobile phone architecture, and also tell a little bit about our research on ISP. So please go to the next slide. So this is the camera in the autonomous car, very typical one. And it consists of 3 main parts which affect the image quality: lens, sensor, and ISP. And these parts, I don't know. This is the sensor, this is the ISP, and this is serializer, which doesn't affect the image quality. But these 3 components are most critical. So the first metric which I want to tell about is detail reproduction, and also cover some more like dynamic range, color, and sharpness. So in photography, when we test cameras, like for mobile phone or for video, we show the camera this type of chart. And the ISP developers, they got pretty smart with that, and they, like VW, you know, remember the story when they tested on the stand the emissions? And it's detected that it was tested and produced very good emissions. The ISP can do the similar thing to this chart. It can understand that I'm looking at the chart, I'm going to draw your lines perfectly. And we are looking like, what we are looking in this chart is basically how far you can see the lines before they become one line. And because of this, we changed to this metrics, which is very similar to DMV. So we put a camera like 10 feet away from this chart, which you can buy on Amazon. It's a $15 chart. And you can put it 10 feet and just take a picture of that. And then you will see what line you can read without confusion. And for example, it's important to understand that what I'm talking about is detail reproduction. It's not sharpness or it's not contrast. So you can see the 3 images here, and the right image has the highest contrast, the middle one has the highest sharpness, but the left one is least sharp, least contrast, but the information is more because you can read, and those you can't. So here we have 3 cameras, which is 30 degree, 60, and 120 FOV, and you can see how far they can see. So this is our system, how it can see on this chart. And when we want to make a new system, we are curious how much further it can see, but not on this chart. We are actually worried about pedestrian and objects. So another metrics for you, you can take 3 lenses over your iPhone and you will see how well iPhone sees, pretty good. And like we have 2 megapixel sensors right now, and we're thinking about 8. Is it worth it? How far we can see, how much more compute we will have, and what is the benefit and downside. And the difference in those 2 sensors, you can see, is the size of the sensor and the size of the pixel. So the 8 megapixel has 4 times more pixels, so 4 times more of information and compute will be required at least. And the pixel is also smaller, so less light capturing, so sensitivity is less. And we need to think how we put the same lens on the 2 sensors and observe the difference. So this is a 30D lens, and we can see that with 8 megapixel, we basically see 1, 2, 3, 4 lines more. So the question is how these 4 lines transfer into distance, and I will cover it a little later. But what does contribute to that? It's the modulation transfer function, which is when we capture the image like this, we want sharp edges, and we measure it using this chart, and we want that to be smooth across the field of view because we want to see periphery and the front at similar sharpness so that we don't have to use different convolutional path to detect something which is on the periphery. And the other metrics is the dynamic range, basically how many shades we can see before we become so dark that noise is so high that we don't differentiate any contrast. And here we explore the dynamic range of the system. And you can actually observe how it actually, like each square here is represented by a point on this graph. So the square goes down, and somewhere it becomes flat. And within each square, we either see the contrast or don't see it. So at some point, like for example here, I already don't see any contrast in there. So this will be dynamic range, is like number of squares which we can capture. And it's a very tricky thing because sensors do lie about that, because the actual system, as you can see, after I measured the dynamic range, is 68 dB, while the sensor says that the sensor is 120 dB, but after the light comes through lens, the sensitivity reduces due to internal reflections, and this is the actual dB. So you can think of like traffic light brightness is like much more than that. It's like more than 100 or 90 dB at least, if you compare like LED and normal Tuscan lights. So this is and the last metrics we care about is basically difference between red and yellow, because its most big point of confusion is in some certain cases you can see the yellow light and think it's a red light, or vice versa. It's a trouble. So, and for this, it's important to see that there is good separation between this like 14 and 15 patches on those chart. And if you see like reference points which represent the actual colors and the points are crossed, this is not a good reliable system. So there should be some color accuracy, but not between, this is not 14 and 15. I think this is orange and yellow. So we engineered the 8 megapixel camera, and I wanted to show some images that we captured with it. It's 8 megapixel on semi-sensors, and we put a pedestrian at 300 meters and started, started to record the same pedestrian with intervals of 50 meters, just to see how it looks at different scale. Can you please play a video, because we actually composed the video how the network actually see the images, because in the network you will be centered around the object which you are trying to detect. And can you play? Yeah, so this is, we tried to center the video of a pedestrian and interpolated the rest from the sequence of images that we captured. So you see that the pedestrian is actually like increasing its detail reproduction, but also the background contrast changes because of the field of view of the camera. So we were curious, especially the track team, like how far we can detect a pedestrian in real situation. And we took can you please back to my presentation? Yeah, we took some dummy targets to the airfield and moved the camera with more precise intervals and recorded the images at every few meters. So we put a deer, a tire, a soccer ball, a child mannequin, and we collected the images from each distance. Yeah, this video is, yeah. So we moved the car, stopped it, take a new image, and recorded, and then we sent these images to labeling team, and we asked them like, how confident what you see is a pedestrian or a deer or whatever, and we sent those series of images, but before that we shuffled them all, so nobody knows what the actual distance was. So you see the difference is quite significant, like 100 and 400. So I'm not sure that this is a pedestrian at the left, but on the right, I am like very confident, more than half. And we sent this kind of survey to a lot of people, and we collected trends. So you see this, this is the distance, and this is how confident I am that what I see is what I see. And we collected a trend, and we saw that, wow, that everybody was around like this, except few people who just were confident at very short distance, and some people were like not confident at all, and the other were just like random. They were just, this is pedestrian, this is not. But so this have to send to vision tests. And these are also maybe wearing glasses reversely, I guess. And I think it's a great actually survey to see if the labeler is in line with the camera. So if the trend is actually quite smooth, then we can also find outliers and learn from them as well. So this is the trend, and this is the trend for 2-megapixel cameras. So you can see, I'm sorry, why? So yes. So you see, this is how the confidence grows. From 600 meters, where we're at 0, we transition to 1 around like 200 meters. And we're at half confidence around like 330 meters. And it's important when you think about this, that this is the effective segment. If we look at this, and we start labeling this type of images, we will see a lot of false positive, and the car will like brake all the time. So we must be very confident, but not like below some confidence level. So thinking about like this segment, we think effective kind of effective measure that we can take. So you can see how different objects, like what is the vision confidence trend for each of the objects. And I'll quickly go through these slides because you can rewatch them later, but it's a valuable information because later I want to link each confidence trend with the vision chart. So you can take any camera and just have some good estimation what it can see and how it can see. So boom. Somehow I'm trying to like next it and it doesn't let me. Sorry? It's okay. So this is comparison of the vision trend for each object, for 2 megapixel and for 8 megapixel. So we build each, so blue is the 8 megapixel. So you can see like on the level of 0.5, this is how much distance we win. So you might think that 8 megapixel, it's like linear equation, right? We stretch, get 2 times more pixels, so we capture more data, so we will be able to capture object of smaller size by 2 or like at the distance twice further, but it's not like that. You're actually gain only a very like around 15 to 20%, depending on the confidence level. So this is, you can study these graphs later, and this green line represents the ratio, basically how much more confident you get when you are at the same distance with the distance based on each sensor. So sweet spot is somewhere here. So we have a lot of much more confident. And yeah, this is, we can just skip this. Yeah, this is just in time how the confidence grows and how faster, how easier and more confident you are with 8 megapixel sensor. So like this is the confidence meter and distance meter. So and the other interesting thing is like at what cost you have detected that. So this is 2 megapixel sensor, and at 2 megapixel we need to detect object at the same distance much less pixels than we need with 8. So at 8, compute will be much more expensive by this curve, basically, by the difference of this curve. So we're thinking, is it worth to upgrade our sensors to 8? And first, just to link with the first part, this is like the difference in lines, and this is the difference in confidence. So you can think that we gained around 25% here, and there is like 1, 2, 3 lines. So around 8, 9%, maybe 10% with each line. Further we will see. So each line gives you 10% in visibility, assuming you are not in the fog, but on a like clear day. And a little bit about our Chinese fleet. It's based on a Toyota Lexus RX 400 in the US. So we are now driving on 7 cameras, and all of them are 2 megapixel. And reminding you of the architecture of the camera, this is how it looks like. And giving you a quick history about the mobile phone architecture. So at first, the sensor and ISP was on one chip, and application processor was another chip on 1 megapixel this timeline. And then around 8 megapixel, which is where automotive is right now, it became a separate chip. And this is what most cars are running. The chip of ISP, which controls the sensor, is the standalone chip, like Geok semiconductor or on many products. And the GPU is a separate unit. But with 8 megapixel, the ISP became a part of application processor on the Qualcomm or like Snapdragon and Samsung as well. So right now, the same thing happening in automotive. The ISP is going to be from single chip. It becomes a part of GPU, and this is how like Orin and Xavier are designed. And instead of having ISP on a camera module, we are moving the ISP into the main brain box. And let's say we put 8 megapixel sensors everywhere. And this will be enormous compute to process 8 megapixel cameras from 8. So we assume that some of those, like left, right, and reverse camera, those cameras can be 2 megapixels, but still use 8 megapixel sensor, but use binning, which is a process of downsampling the image on sensor, which is quite distractful for the image quality. So, but on the sides, the image quality is less kind of important. And ISP becomes a part of GPU compute unit, and we are able basically to go around and collect raw images on our drive for training, and we can have two pipelines, one for training and one for labeling, because training pretty much uses different laws of pre-processing than people. So we can, if we have the raw data, this is what we are allowed to do. And the last 2 minutes I have, I will talk about the ISP. So this is how sensor captures the image. It doesn't capture colors at each location. And it also has a...
Just so you know, you have more. That's how much time you have to talk. There's still 5 minutes.
Thank you, thank you. Oh, okay, then I will go back. So in sensor, each captured value is 24-bit. So it means that it can reach up to 20 million in value. And the most networks are already trained on the images which are pre-processed. So those are 8-bit images. We have much more data in the sensor. So what ISP does, it basically takes the 32 or 24-bit and downsamples it to, it's not downsample, it's quantizes it, quantizes it to 8-bit. And ISP decides what is important and what isn't. So, and in our human vision, ISP is similar to retinal ganglion cells and bipolar cells together, because the human doesn't send all the information to his brain, like all the pixels. He basically sends the differential signal. And you can Google and watch about ganglion cells. So it's basically a DSP, which looks at color difference or brightness difference and sends the change in this distance to the brain. So it's similar to convolutional kernel of low pass and high pass, basically. So, so in RAW, the image comes like this in planes and has 24-bit, and then it goes to 8-bit. So here it's tone mapping or ISP like pipeline. And as I said, we prefer to put as much RAW as possible to CNN and different for human, because human wants to see color properly. And we developed ISP for like our back office, so to say, which we already connected to Sony on Semi and connecting to OmniVision sensors. And we are comparing them with on Semi ISP, which is built in right now. So we are a little bit better on the, from the same raw image, we can produce a couple more lines, maybe like 15% of visibility improvement just by using a different demosaicing process. So more pictures of this ISP. And we also compared it with Orion and Xavier. It's actually outperforms them, but I cannot share the images of Orion right now. So yeah, we're comparing with Onsemi software ISP, and it's pretty few steps ahead, which is considerably like upgrading the sensor resolution to like by 50%, I would say, because it's like 2 lines rather than 4. Yeah, so yeah, I made it on time. Yeah. So yeah, thank you. Yeah. Please let's.
Okay, great.
Yeah.
I wish you would have known you had more time, but that's okay.
Yeah. But
anyways, that gives us more time for questions.
I just there were so many slides. I was worried.
Yeah, that's okay. That's okay. So, any questions? Hopefully, we have quite a bit. Start here. Wait for the mic, please. Introduce your name and company too, just as a reminder.
Thank you. My name is Liang Ma. I'm from Stone Ridge. You mentioned that for 8 megapixel camera image, the ISP is moved to GPU, right? So can you elaborate on this change? Why do you make this change? What is the advantage of moving ISP into GPU?
Yes.
Thank you.
Yeah, sure. So there are several advantages of this. So one important advantage is the ISP is the part which gets the most hot. So it goes up to more than the boiling point in like around 120 degrees sometimes, and it requires cooling. So it can use the cooling system of the GPU. And the other thing, if you put the camera under the windshield, then you can't dispose heat from there. So it's much better for the ISP to heat up somewhere where there is cooling system. And the second is that sensor also gets heated, and the image quality goes very bad if you heat the sensor up. And also from data point of view, if we collect, from infrastructure point of view, if you collect the data at the same bus as GPU, you can capture raw data. And if you have ISP, not every ISP will give you the chance to capture raw data. So it's a very good, and the other thing, I can use the GPU as a farm to pre-process my raw images when I want to train on raw data. So I can take some ISP with some certain settings and take my training set and pre-process the whole set using the same ISP condition. But if I have a chip which is like what it is in the camera right now, you can't use this for a render farm. So if you have a training set, you will not be able to pre-process it, but you need to do it a lot. So, and you have like several million images in your training set. Each parameter you change, you need to pre-process the data. And you will need to pre-process this million images 100 different ways. It will be impossible to solve if ISP is just on a chip and we need to upload image to the chip and download it back. So GPU gives us to do it in just by how many clusters you put. You can grow it infinitively. So it's very good for bridging machine learning together. And the other thing, you can output images at different stages of process and feed them into pipeline at the network at different stages of pipeline, which is totally impossible when you do it in ISP, because ISP is just in and out, and nobody knows what happens there. So if the image, like if I miss the traffic light, I will try to debug. Is the ISP didn't process it and just put it down, or the sensor didn't even capture the state? And if it's lost within ISP, there is no way to hack inside, because it's just like you put data in, you take data out. There is, if I can control each step, much more like safe system, so to say.
Another question, here we go. Oh, sorry, okay.
Yeah, hi, this is Gaurav from RightCell. So when you talked about the initial experiment, when you're looking at the distances that you can detect an object at, It brought me to the Johnson's criteria. It's like a very old criteria where you're looking at the number of pixels that might be required to detect, identify, and classify an object. Are you thinking of using the experiments that you did to sort of create a new standard for like how many pixels that you require to sort of detect an object? Is that something that you're interested in? Some kind of standardization that you would release?
I just released it. So basically, I told you these graphs telling you how many pixels you need to detect an object, because it's even more precise than the network, because it came from the consolidated opinion of labeling, and not just 0 to 1, like see a car or not see, but we even give them like how confident they are. So this trend is very, very like much more precise than machine learning can follow. So machine learning just has to represent this trend, but this is how labeling team gave us their kind of whole vision there. So we harvested for their confidence, basically. So,
Okay.
but pixel size is there too. So because it was easy to count, so we just put a ruler and counted.
Yeah, so one other thing is sort of real world performance. So you took one case where you're looking at that object, but when you go in a real world, when you're driving, there's like vibration, the pixels are not often clear. Did you also look at that as well?
No, it's actually, this is in perfect, in space, basically, what I'm giving you. But for example, at night, everything will not follow this law, because the visibility will be determined by the strength of your light beam. And the fog will affect it in quadratic, kind of inverse quadratic way. And there is so many other things, like flare from other cars, presence of bright objects, dirty lens. It's not about this. It's just like hypothetical maximum, basically.
Next question.
Thank you. I really enjoyed your talk. My question is focused on processing high-resolution imagery. So there are benefits for 8-megapixel imagery.
By the way, name and company, sorry.
Oh, sure. I'm Shravan from Hyperspec AI. So my question is focused on the machine learning models that are capable of processing image data today require you to downsample the images a certain amount. So how do you retain the benefits of the longer range of the 8-megapixel resolution while simultaneously being able to run this real time?
I didn't get the question itself. So how do I incorporate downsampling of the images into machine learning network?
So most machine learning models require you to reduce the resolution of the image before you could feed it into the network.
Yeah.
And the benefit of the higher resolution image is you can see the things that are further range. So how do you create like regions of interest to feed it into that model?
It depends how you train the model. You can train it at any resolution. So we basically have a region of interest which we cut the sky and some area of where we don't look for objects. So, but then we have a certain image size, and then we just train on that image size. So you don't have to necessarily downsample it. But if you need to downsample it, we have many ways to do it in ISP or
So I think you
POSA.
answered my question. You use regions of interest to feed into the model.
Is really just a crop. Just a crop.
Thank
I
you.
also think he said they have different decimation techniques as well, correct? I don't want to put words in your mouth, but
We have, so we can do it inside of the ISP, we can do it on sensor, and we can do it also in GPU. And we have a study which sees, it's very nice to take this chart and run it through all this, and I have this at custom request, I can also send the chart, and you will see how much resolution you will lose if you downsample and where. So if you downsample at later, it's always better than you downsample it in the raw. So the binning is crushing relative kind of information, and the resolution reduces like one line difference in that chart, basically.
correct. Okay. Yeah, I think we got one more question. We can do one more.
So, Mark Pattison from Valio, just to piggyback on that report you did on the 2-megapixel versus the 8-megapixel. Was there an assumption that the lens quality increases as well when you go to an 8-megapixel, or are we saying same quality lens? Because it takes three things, as you mentioned, right?
Yes. I'm not a lens expert, but I'm a lens freak. So.
Is that a song?
No, but I like to see different lenses in cinematics and measure their quality and collect them. So what we did, we basically used an 8 megapixel lens on the both of them, because for 8 megapixels, since the pixel is smaller, you need much better coating to not make the light diffuse into neighboring pixels. So it requires much more precise lens. But for working with it on 2 megapixel sensor is fine, because the same image circle, and it's basically has it won't make it worse. Basically, it will focus the light inside of each pixel properly. So we did as much apple to apple as possible, you know. But if we choose a 2 megapixel, put it on 8, then we will see like a 2 megapixel image on the 8, because it basically will create a low pass filter.
Let's do one last question. I think you had your hand up.
Stephen Kanzler, ZF. Have you considered supersampling techniques to increase the range even further?
Supersampling? No. Supersampling is too expensive in hardware, and it doesn't give you much more information, I guess. But I don't. I think it's more expensive than benefit to do.
Okay.
Yeah.
All right.
Yeah.
Well, thank you. Great talk.
Thank you very much.
Very interesting.